In October 2025, Nvidia CEO Jensen Huang told reporters that U.S. export controls had taken his company's share of China's AI chip market from 95% to, in his words, zero. He said it plainly, almost casually, the way you might describe losing a set of car keys rather than losing access to the second-largest technology market on Earth. 6 months later, Bernstein Research published a chart that told a slightly different story. The chart, which was later reprinted in The Economist and the South China Morning Post, showed Nvidia's projected share for 2026 at roughly 8%, down from 39% in 2025. Huawei's share sat at approximately 50%, translating to an estimated $12.1 billion in annual sales. Now, neither 0 nor 8% is really the number that matters most here. What matters is the direction. In 2019, before the first export controls landed, Huawei had no meaningful share of China's AI accelerator market. None. It was not a player. It was not a contender. It was building telecom infrastructure and smartphones, and the idea that it would become the dominant supplier of artificial intelligence chips to Chinese data centers would have sounded like a stretch even to Huawei's own engineers. By mid-2026, Huawei dominates the market. And the policy that was specifically designed to deny China access to leading-edge AI compute is the single biggest reason that market exists in the form it does today. The standard way people talk about U.S. chip export controls is binary. Either they are working or they are not. Pundits line up on one side or the other, and the debate plays out like a sports argument where everyone already picked their team before the game started. But the evidence available in mid-2026 says something more uncomfortable than either side wants to hear. The controls are working, and the controls have backfired. And both of those statements are supported by the same data, sometimes from the same paragraph of the same analyst report. The distinction between the two outcomes is arguably the most important technology policy story in the world right now, and understanding it requires looking at specific numbers rather than choosing a narrative. On the side of the argument that says the controls are working, the evidence is genuinely strong. The Council on Foreign Relations published an analysis in December 2025 that laid out the performance gap between the best American AI chips and the best Chinese ones. At that point in time, the best U.S. chips were approximately 5 times more powerful than Huawei's best offerings in total processing performance. And the gap was not closing. By 2027, CFR projected it would widen to 17 times. Huawei's own public roadmap, which the company itself released, showed that its next-generation chips, arriving in 2026, designated the Ascend 950PR and the Ascend 950DT, would actually be less powerful than its current best chip, the 910C. That is not a typo. The next chips are weaker than the current chip. The reason is a manufacturing ceiling that we will get to, but the takeaway is clear. The performance ceiling is real. SMIC, China's most advanced chip maker, is stuck at 7 nanometers. The controls are, by the metric they were designed to target, holding the line. On the side of the argument that says the controls have backfired, the evidence is equally strong and in some ways more alarming. Huawei went from 0 to 50% market share in under 5 years. In May 2026, China certified 9 domestic AI processors for government procurement, meaning that Chinese government agencies buying AI compute now have 9 homegrown options that did not exist when the controls were first imposed. Bernstein projects that China will produce more domestic AI chips than its own demand requires by 2028, with domestic sales growing at 74% annually. And captive markets, markets where domestic buyers have no choice but to buy domestic products, have a historical tendency to close capability gaps over time. The question is not whether they close them, it is how much time the closing takes. To understand how these two contradictory outcomes happened simultaneously, you have to walk through the policy timeline and see how each restriction reshaped the market it was trying to control. The first restrictions hit Huawei directly in 2019 when the U.S. government added the company to what is called the Entity List. That designation cut Huawei off from American software, American components, and, critically, American chip design tools, the electronic design automation software made almost exclusively by 3 American companies that every advanced chip maker in the world uses to design its processors. Without those tools, Huawei could not design chips using the most advanced architectures. Without access to Google's Android services, Huawei could not sell competitive smartphones outside of China. The designation was a targeted strike at a single company, and it was devastating in the short term. Huawei's smartphone business, which had been on a trajectory to overtake Samsung as the world's largest, collapsed. Its revenue fell by nearly 30%. Entire product lines were discontinued. But the Entity List designation also did something that its architects may not have fully appreciated at the time. It sent a signal to every other company in China, every cloud provider, every AI startup, every state-owned enterprise, that dependence on American technology was not just a business risk, but a strategic vulnerability that could be weaponized at any moment. And that signal would echo through every procurement decision, every research budget, and every government directive made in the years that followed. In October 2022, the Bureau of Industry and Security imposed a much broader set of controls. These were not targeted at one company. They were sweeping restrictions on advanced semiconductor exports to China as a whole, blocking chips above certain performance thresholds, and, just as importantly, blocking the equipment needed to manufacture them. This was the move that changed the architecture of the entire market. Nvidia, which had been selling its most powerful chips freely in China, was suddenly unable to ship its flagship products. The company responded the way any company would. It designed export-compliant chips. First the A800, then the H800, then the H20, each one deliberately throttled in performance to stay below the control thresholds that the Bureau of Industry and Security had set. China kept buying whatever Nvidia was allowed to sell, because even a throttled Nvidia chip was better than the domestic alternatives available at the time. The H20, which was Nvidia's most popular China market chip, shipped more than 1 million units from late 2024 onward. It was a worse chip than what Nvidia could have sold without restrictions, but it was still good enough to train and deploy AI models, and Chinese buyers consumed it at enormous scale. Then 2 things happened in close succession that turned a gradual market shift into a hard break. In December 2025, President Trump announced the Nvidia H200. The most powerful AI chip ever approved for export to China, would be cleared for sale, but with significant conditions attached. There would be a 25% tariff, there would be U.S. government testing requirements. The Department of Commerce formalized the rule on January 13, 2026, and for a brief moment, it looked like Nvidia might be able to claw back some of its lost market share with a chip that was genuinely competitive at the high end. But Beijing had a different idea. The Chinese government responded by encouraging domestic buyers to boycott the H200 entirely. The signal was not subtle. It was not a suggestion buried in a policy memo. It was an explicit directive communicated through the channels that Chinese technology companies understand perfectly well. Buy Huawei. This was the inflection point. The export controls had already been pushing Chinese procurement toward domestic alternatives for years. Beijing's boycott directive converted that gradual push into a mandate. By mid-2026, Nvidia was not just restricted in what it could sell to China, it was unwelcome. Jensen Huang himself, during a visit to Beijing in May 2026, admitted publicly that Nvidia is, in his words, no longer competitive in the Chinese data center market. He said this while eating noodles at a local restaurant, mobbed by Chinese fans who admired his company's technology even as their government was systematically replacing it. It was one of the stranger images in recent technology history, a CEO simultaneously beloved and exiled. So what exactly did Huawei build while all of this was happening? The answer is both impressive and limited, and the distinction between those two qualities is where the real story lives. The Ascend 910B, which became Huawei's mature workhorse chip, delivers roughly 256 teraflops at FP16 precision, with 64 gigabytes of HBM2E memory. To put that in context, those specifications place it in approximately the same performance class as Nvidia's A100, which is a chip that Nvidia released in 2020. The next step up, the Ascend 910C, approaches the Nvidia H100 on paper specifications, but CFAR's analysis found that the H100 is 60% better in real-world performance when you move past the spec sheet and into actual workloads. The 950 PR, which is arriving in 2026, trades single-chip performance for system-level scale, which is another way of saying it is not actually a faster chip than its predecessor. Huawei's strategy is not to match Nvidia chip for chip. The company's engineers understood early on that they could not win a head-to-head comparison on individual chip performance because they did not have access to the manufacturing processes that would make that possible. So instead, they chose a different approach. They decided to wire thousands of inferior chips together and compete on aggregate compute, total system-level performance rather than per-chip performance. The Atlas 950 SuperPod connects 8,192 Ascend chips into a single cluster. Huawei claims this system beats Nvidia's NVL144 on total compute, total memory, and total bandwidth through sheer brute force. The numbers Huawei cites are dramatic: 56.8 times larger in scale, 6.7 times the total computing power, 15 times the memory capacity. These are company claims measured on favorable benchmarks, not independent third-party measurements, and they should be understood with that caveat. But the approach itself is coherent. If you cannot build the best chip, you build the biggest cluster, and you compete at the system level rather than the component level. There is historical precedent for this approach working over time. The software stack matters just as much as the hardware, and possibly more. Nvidia's dominance in AI computing has never been purely about silicon. It has been about CUDA, the programming platform that Nvidia built over nearly 2 decades, which became the standard language that every AI researcher, every machine learning engineer, and every data scientist learned to write their code in. CUDA is the moat. It is the reason that even when a competitor builds a chip with comparable specifications, customers do not switch, because switching means rewriting every piece of software they have ever built. Huawei understood this problem and attacked it directly. They built CAN, Compute Architecture for Neural Networks, as their equivalent of CUDA. They built MindSpore as an open-source deep learning framework intended to compete with Google's TensorFlow and Meta's PyTorch, And critically, they built a CUDA-compatible programming layer that lets developers port their existing CUDA code to Huawei hardware without rewriting it from scratch. The moat that Nvidia spent 20 years building is the moat that Huawei is trying to drain, and the CUDA compatibility layer is the pump. But here is where the market share story and the capability story diverge, and the divergence reveals the most important detail in this entire landscape. Huawei's Ascend chips can run inference, which means serving a trained AI model to users, letting people interact with a chatbot or run image recognition or process natural language at competitive scale. Inference is what most commercial AI workloads actually consists of. When you ask an AI assistant a question, when you use an AI-powered search engine, when your phone translates a sign in a foreign language, that is inference, and Huawei can handle that. Training is a different problem entirely. Training means building the model from scratch, feeding it billions of data points over weeks or months of continuous computation, adjusting billions of parameters, recovering from hardware failures without losing days of progress. Training is the hard part. Training is where the frontier of AI capability actually moves. And on training, the Ascend ecosystem has a documented and significant failure that undercuts the entire market share narrative. DeepSeek, which is one of China's most capable and most closely watched AI laboratories, attempted to train its R2 model, a next-generation reasoning model that was expected to push the boundaries of machine reasoning on Ascend 910C chips. They did this under active government encouragement. Beijing wanted a showcase. It wanted proof, visible and undeniable, that Chinese hardware could train a frontier AI model from scratch without any reliance on American silicon. The political value of such a demonstration would have been enormous. It would have validated every yuan spent on domestic chip subsidies and every procurement directive steering buyers away from Nvidia. The effort failed. It did not fail once and succeed on a second attempt. It failed repeatedly across multiple training runs in ways that forced DeepSeek's engineers to conclude that the Ascend platform was not ready for this task. R2 training reverted to Nvidia hardware. The reasons were rooted in the software stack rather than the silicon itself. CAN, MindSpore, the CUDA compatibility layer, all of these tools are functional enough for deployment, for running a model that has already been trained and serving its outputs to users. But training is a fundamentally different engineering challenge. A training run for a frontier model can last weeks or months of continuous computation across thousands of chips. A single software crash during that process can cost days of work. An intermittent memory error can corrupt an entire training run and force engineers to roll back to a checkpoint that might be hours or days old. The interconnect software that coordinates communication between thousands of chips has to handle failures gracefully, rerouting computation around dead nodes without losing data. The software has to be, in a word, bulletproof. And Huawei's software is not bulletproof yet. It is good enough for inference. It is not good enough for training. And that distinction turns out to be the most consequential gap in the entire Chinese AI hardware ecosystem. This matters enormously because training is where the frontier moves forward. A country that can deploy AI models but cannot train them is fundamentally dependent on whoever trained the model it is running. It is the difference between owning a car and owning the factory that builds cars. China's top AI labs, DeepSeek, Alibaba, Baidu, ByteDance, still rely heavily on Nvidia hardware for training. An estimated 75% of the chips powering AI model training in Chinese data centers still run on Nvidia's CUDA platform. The market share numbers that show Huawei at 50% describe a deployment reality. The training dependency that shows Nvidia still dominant describes a capability reality. They are measuring different things, and confusing them leads to conclusions that are wrong in both directions. The reason the performance gap is not closing, and in fact is widening, comes down to manufacturing, and specifically to a company called SMIC. Semiconductor Manufacturing International Corporation is China's most advanced chipmaker and Huawei's primary fabrication partner. Its most advanced production process is a 7-nanometer class node, achieved without the extreme ultraviolet lithography machines made by ASML in the Netherlands that every other leading chipmaker in the world depends on. SMIC achieved 7 nanometers using older deep ultraviolet equipment with multi-patterning techniques, essentially exposing the silicon wafer multiple times with slightly different patterns to achieve finer detail than the equipment was originally designed to produce. Each additional patterning pass adds cost, adds time, and adds opportunities for defects. It works. It is a genuine technical achievement, one that many industry observers said was impossible when the export controls on EUV machines were first imposed. The assumption was that without EUV, China would be permanently stuck at 14 nanometers. SMIC proved that assumption wrong. But the process is slow, it is expensive, it is difficult to scale to high volumes, and it produces yields, the percentage of chips on a wafer that actually function correctly, of only 20 to 40%. That means for every 10 chips SMIC fabricates, 6 to 8 of them go in the trash. The economics of that failure rate ripple through every product Huawei builds on SMIC's lines. TSMC, the Taiwanese company that manufactures chips for Nvidia, Apple, and most of the world's leading technology companies, gets yields of 60% or higher on far more advanced processes. TSMC is at 3 nanometers and moving to 2. The gap between SMIC and TSMC is 2 to 3 full process generations, and each generation represents a roughly 30 to 50% improvement in performance and power efficiency. Tech Insights, a firm that specializes in tearing apart chips and analyzing their construction under electron microscopes, confirmed something particularly telling about the Ascend 910C. It still contains CPU management dies, small subsidiary chips that handle housekeeping functions that were fabricated by TSMC, dating to approximately 2020. TSMC has now halted all production for Huawei. This means that every future Ascend chip depends entirely on SMIC, with its lower yields and its older process technology. And this is the binding constraint that explains why Huawei's 2026 chips are not advancing past the 910C. According to Huawei's own public roadmap, the 950PR and the 950DT represent a regression in per-chip performance compared to the 910C. They are designed for cluster-scale computing, not single-chip power. The first Huawei chip planned to actually exceed the Nvidia H200 in performance is the Ascend 960, which is scheduled for the fourth quarter of 2027, meaning it likely will not be widely available until sometime in 2028. Meanwhile, Nvidia's roadmap is not standing still. Blackwell is shipping now. Rubin is on track for 2026. Vera Rubin follows in 2027. By the third quarter of 2027, CFR projects that the best Nvidia chip available will be 26 times the performance of the best Huawei chip released in the same period. The performance gap is not holding, it is accelerating, because Nvidia can advance at the pace of TSMC's manufacturing roadmap, and Huawei cannot. But here is the honest counterargument, and it deserves to be stated plainly rather than dismissed. Capability parity is not the only metric that determines strategic outcomes. A country that controls 50% of its own AI chip market, even with chips that are 5 times slower than the frontier, has something that no export control can reverse. It has independence. If every major Chinese cloud provider, every government agency, and every significant AI laboratory is running production inference on Huawei hardware, then the dependency for Nvidia for deployment is broken. The dependency for training remains, yes, but training is a smaller fraction of total compute demand. Inference accounts for 80 to 90% of commercial AI workload. The thing that most AI systems spend most of their time doing is the thing that Huawei can already handle. And Bernstein's projection opens a second-order possibility that the original policy was never designed to address. If China produces more domestic AI chips than its own market requires by 2028, then China becomes a potential AI chip exporter. If Huawei can sell Ascend-based systems to countries that cannot access or cannot afford Nvidia hardware, Belt and Road nations, the Global South, sanctioned states looking for alternatives to Western technology, then the export controls did not just build a domestic champion inside China, they built a potential competitor in markets that the United States was not watching and was not defending. The chips would be slower than Nvidia's best. They would be less efficient. They would require larger clusters to achieve comparable performance. But they would be available, and they would be affordable, and they would come without the strings that American technology increasingly carries: end-user agreements, export license requirements, the ever-present possibility that Washington might change the rules and cut off supply at any moment. For a government in Southeast Asia or Africa or Central Asia trying to build out its first AI infrastructure, trying to stand up its first national data centers and train its first domestic language models, available and affordable and politically uncomplicated beats fastest and most expensive every single time. That is not a hypothetical market. That is a market of billions of people in dozens of countries, and it is a market where the United States has no competing offer at the price point Huawei can reach. The performance gap is real. The market outcome is also real. And the market outcome is the one that compounds over time, because markets generate revenue. Revenue funds research. Research closes capability gaps, and closed capability gaps generate more market share. That is the cycle that export controls inadvertently set in motion. So where does this leave us? The U.S. export controls on AI chips did exactly what they were designed to do. The frontier capability gap between American and Chinese AI hardware is large, and it is growing. SMIC is stuck at 7 nanometers. Huawei's next chip is weaker than its current one. The training dependency on Nvidia persists across China's most important AI labs. By every performance metric that the controls were designed to target, the controls are holding the line. And the U.S. export controls on AI chips did the precise opposite of what they were designed to do. In 5 years, Huawei went from irrelevant in AI compute to the dominant supplier in the world's second-largest AI market. A coalition of over 2,000 Chinese firms is now targeting 70% semiconductor self-sufficiency by 2028. Beijing mandates domestic procurement. Nvidia's CEO, standing in Beijing, eating noodles, surrounded by admirers, admitted publicly that his company can no longer compete in China. The market that the controls were supposed to starve is thriving. It is thriving on inferior hardware, but it is thriving. Both of those paragraphs are true. Both of them are supported by the same evidence, often from the same sources. The policy slowed the frontier and accelerated the foundation. It denied China the best chips and handed Huawei a captive market worth $12 billion a year. It widened the performance gap and narrowed the market gap. It achieved its technical objective and undermined its strategic one. The question that remains is not whether the controls worked, because by now it should be clear that asking whether they worked is the wrong question. The right question is which outcome matters more over the next decade, the performance gap or the market share, and whether anyone in Washington modeled the second outcome before they pulled the trigger on the first. Huawei is winning the Chinese market today with chips built on 7-nanometer technology. But SMIC is not standing still. Reports from multiple analyst firms suggest that SMIC is pushing toward 5-nanometer class production using the same multi-patterning deep ultraviolet techniques that nobody in the semiconductor industry thought would work at that scale. They thought 7 nanometers was the wall. If SMIC breaks through the 7-nanometer ceiling without a single extreme ultraviolet lithography machine from ASML, if they figure out how to pattern features that small using equipment 2 generations behind the cutting edge, then the performance gap that CFR projected starts closing on a timeline that no export control was designed to handle. The controls assumed the manufacturing ceiling would hold. They assumed that 7 nanometers was the end of the road for a foundry working without EUV. They assumed that the physics would do the enforcing that policy could not. If that assumption turns out to be wrong, if SMIC's engineers find a way through the wall the same way they found a way to 7 nanometers when nobody thought they could, then every projection about the performance gap, every timeline about when China catches up, every model that policymakers built their decisions on starts shifting in directions that nobody in Washington planned for. The question now is whether the ceiling holds, and nobody on either side of the Pacific knows the answer.